Okay. Okay. So let's start where we left. So in the exercises, we looked at this Polyakov p-brain action. I'm sorry, here it was saying D2 sigma, but for the p-brain is dp plus 1 sigma. And with the cosmological constant term, and I say the cosmological constant is proportional to p minus 1. So let's go back to strings. So this is S1. This is T2 sigma. And there is no cosmological term. This is proportional to p minus 1. So that's the Polyakov string action, which is equivalent under integrating H alpha beta under solving H alpha beta by the equations of motion is equal to the Nambu-Goto action. So what are the symmetries of this action? So first we'll start from local symmetries. And the first one is reparametrizations of the worksheet. Reparametrizations of the worksheet. So like diffeomorphisms of the worksheet. So if I take sigma tilde alpha, which is some f alpha of sigma, and then I take, so x tilde mu of sigma tilde has to be the same as x mu of sigma alpha, right? Sigma tilde denotes, I'm just using, so on this worksheet I can use this tau and these sigma coordinates, or I can use to describe the same worksheet. I'm trying to do the drawing. I can use another tau tilde and I don't know, some sigma tilde coordinate. But if I'm in the same point, so if I have the transformation between tau and tau tilde and sigma tilde, then this the point that corresponds to this point should have the same embedding coordinate, right? And then H alpha beta transforms as the metric, so H tilde alpha beta is equal to H gamma lambda d sigma lambda d sigma tilde alpha d sigma, sorry, well, gamma lambda d sigma tilde beta. So it transforms as it should. So these are reparametrizations, and it's not hard to show that because everything is covariant. So these are like diffeomorphisms on the worksheet, right? The worksheet is this two-dimensional theory, and these are diffeomorphisms on the worksheet. Everything is covariant, so it's simple to show that. Here by sigma, I mean tau and sigma, right? You understand? The second is wild transformations. So as somebody asked, this is the same for the P. The P-brain action also has this reparametrization with the P plus 1. So the P plus 1 reparametrizations. But what it doesn't have is wild transformations. So wild transformations In well transformations, we keep maybe I should, well. So what we do is H alpha beta goes to e to the omega, or to omega, what did I use? E to the omega so I rescale H alpha beta by some overall function. And this is local. This can depend on sigma alpha. And the action is invariant because here you have the inverse metric. So this goes with the power of e to the minus omega. And this is a determinant. So it has e to the 2 omega, and the square root has an e to the omega. So this e to the omega cancels this e to the minus omega. But you see that if this was something in more than 2 dimensions, this will have more powers of omega. So this is something particular about the 2-dimensional action. While this is general, so this is only for, only for p equals 1, which is a case we'll discuss until the very end. I will discuss difference, right? So I'm talking about the string action. And if G mu nu, this is not very, if we are in flat space time, then the action has also Poincaré global Poincaré transformations, which are rotation, boosts, and translation. So x tilde mu equals a mu nu x nu plus b mu. So rotation, boosts, and translations. This is only if you're in flat space. Yes? Right, yes. Yeah, that's harder to characterize, but yeah. Okay, so what are the equations of motion? So equation of motion for our fields. Our fields are this x mu. So we have this, so mu goes from 0 to d minus 1. We have these d fields, which from the point of view of the worksheet, they are scalar fields. So they are just d copies. This index mu is d copies. So these are the, let me write it, equations of motion for the d scalar fields x mu. So again, when I say scalar, I mean from the point of view of the worksheet. So from the point of view of the worksheet, mu are more copies. But from the point of view of this 2-dimensional field, it will be a quantum field theory. This is a theory of the scalar fields. So how do I find the equations of motion? Given the Lagrangian, the usual thing, right? Derivative of the Lagrangian with respect to x mu, and then this d alpha minus, minus derivative of the Lagrangian with respect to x mu, right?
When you say from the point of view of worldsheet, let me see if I understood it correctly. So it means if it's not from the point of view of worldsheet, it can take the maximum spin of d minus 2.
So if it's not from the point of view of worldsheet, this is a vector. It has a vector index. So from the point of view of space-time, these are, well, it's actually the derivative of this that will be vector, but there is this index, there is this vector index. So we'll work in flat space. So these are this is a vector index in flat space. But from the point of view, in space-time. But from the point of view of the worldsheet, this is just a copy. It's like when you have, I don't know, phi I, and I goes from 1 to n, and you have a theory of scalar fields, that's the same. A theory of d scalar fields, x mu. That's from the point of view. So from the point of view of the worldsheet, these are like some phi I. And this I goes from 0 to d minus 1. Yes. Yeah. So here, this is for flat space, right? So here I don't have gravity. But yeah, otherwise it's not, that's not a symmetry. I mean, what he said, if you are in some background metric, these transformations are whatever are the symmetries of that metric. Yeah, so, we'll see that. Let me, yeah. But, yeah, you can ask again in a couple of classes, and, yeah. Okay, does the Lagrangian depend on x mu? The Lagrangian certainly depends on the alpha x mu. Does it depend on x mu? No, yes. Well, if this metric is generic, this will actually be a function of the coordinates. So this will depend on x mu in general. But now let's take for a couple of classes, let's take g mu nu equals eta mu nu. So we will just be looking at strings moving in flat space. To quantize and everything, we'll be looking at strings in flat space. So then the Lagrangian doesn't depend on x mu. And what we get here is the derivative of the Lagrangian with respect to the alpha x mu. So we get the alpha, and then this is square root of minus h. That's a factor of 2, square root of minus h alpha beta, d beta x mu, right? This is this. So this should be equal to 0. And this is just a covariant Laplacian. So covariant with respect to, so if I see this as a metric in this two-dimensional space, but two-dimensional worldsheet, then this is just a covariant Laplacian. So I mean, this is the alpha, where I raise and lower indices with this h alpha beta. So this is just the equation of motion for forget about this mu. And again, if instead of x you put phi, you're more used to it. So Laplacian of phi equals 0 is the equation for a free scalar field, right? So what we have is the free scalar fields. So the embedding coordinates, now they become in this two-dimensional worksheet. They are scalar fields, and if the strings are in flat space, then they are free scalar fields. If it's not flat space, then here you will get something, and it's some horribly or non-horribly, depending on how horrible is the metric, but some interacting, these are the free interacting fields, where the interaction is related to derivatives of the metric with respect to x mu. Yes?
Is there a physical implication of the fact that the embedding coordinates become free scalar fields of the worksheet? How are you going to do this?
Well, I mean, the way we saw it is so the way we saw it is from the Nambu-Goto action to the Polyakov action, and these were the embedding coordinates, and now these are scalar fields. And actually, so this is the point that I was. Yeah, this is a point I will say it, but let me say a few things and then we'll come back to that. But I could have said again, I could have started from the Polyakov action. Okay, this is an action on the worksheet. You have these d scalar fields, and depending on how this depends on x, then you get an equation of motion. Like you have no idea how to solve in general, but if you're in flat space, then these are the free scalar fields. And I could have said, okay, we could have started from that. But no, we started from the. So maybe I should start from that, because I got many questions about the Nambu-Goto being equal to the Polyakov, and so starting from the Nambu-Goto, then you didn't like the fact that so at the classical level it's easy to see, but quantum mechanically there is no way to quantize the Nambu-Goto, and then there are many questions that arise. But now, and actually the interpretation of this as embedding coordinates sometimes is not even possible. So this is more fundamental. So these are my d scalar fields. So string theory is a theory of these d scalar fields with that action. If you want, that's string theory. And the fact that I can interpret this as embedding coordinates is possible only in some simple backgrounds, like flat space, or, I mean, so if I have an equation, horrible equation, to realize that that comes as the equation of motion with some space-time metric, that's not always possible. But again, so we'll keep working with this as embedding coordinates. So again, let me say a few things and I'll come back to that. A few more things and then I'll come back to that. And there were also the constraints, so which was the equation of motion for H alpha beta. So H alpha beta it plays this role of the worksheet metric, but it's actually some auxiliary field. So we have also the derivative of the Lagrangian with respect to H alpha beta down. We should be equal to 0, and this was the first thing you had to do for the exercise to show that the Polyakov action was equal to the Nambu-Goto action. So, I mean, this is easy to do. So from this derivative, let's define the energy momentum tensor, which is so when you do the derivative of the Lagrangian with respect to H alpha beta, you get a factor of minus T over 2, you get a factor of square root of minus H. So all this is to get rid of that. And if you do this calculation, what you get is that T alpha beta is the alpha x mu, the beta x mu, minus 1/2 of H alpha beta, H gamma lambda, di gamma x mu, di lambda x mu. And here I'm putting indices mu up and down. This I could have done with a generic metric, space-time metric. So this is true. I mean, this derivative is true for any G mu nu. G mu nu doesn't depend on H, and there is no H dot, so this is generic. So the constraint is that T alpha beta is equal to 0, since this is proportional to this derivative, and this derivative have to be 0. So the constraint is this. Let me leave this Polyakov action. So now let's see what these scalar fields look like. And for that, let's use reparametrization symmetries, or let's use all the local symmetries. To simplify our lives, let's put it this way. And I can use, so there are reparametrization symmetries, I have 2 of them. So I can do a sigma tilde, which is a function of tau and sigma, and a tau tilde, which is another, I don't know, function 0, function 1 of tau and sigma. To fix 2 of the, so H alpha beta is a symmetric, a 2 by 2 symmetric matrix, and I can fix H alpha beta to be so I can H01 to be 0 and H00 to be minus H11, such that H alpha beta is e to the call it e to the omega eta alpha beta. So eta alpha beta is minus 1, 0, 0, 1. So this satisfies these two constraints. I mean, if you look, so if this is confusing, if you go to the point particle, there was E that was minus the square root of x dot square m square. And here I can choose tau. I can use the tau reparametrization invariance to make E equals 1, for example. That's a gauge choice, a diffeomorphism, choosing some tau such that this is equal to 1. Well, this is similar. So choosing some tau and sigma such that the metric, this H alpha beta, our auxiliary fields, there's just this one parameter in this auxiliary field. And this is in general a function of tau tilde and sigma tilde, right? And then I can use Weyl symmetry, Weyl rescalings.
You can take any gauge that has 1 degree of freedom left for here. For example, diagonal entries are 0 and octagonal entries are
Yeah. 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 And then you can use Weyl rescalings to get rid of, I do H tilde alpha beta equals to e to the minus omega H alpha beta, and this is then eta alpha beta. So this e to the omega, this overall thing, I can reabsorb by doing a Weyl rescaling. So by using the 3 local symmetries that we have, we can fix the 3 components of the metric to be minus 1, 1, and 0. And then our life is very simple because this covariant Laplacian is just an ordinary Laplacian. So an ordinary Laplacian, an ordinary second derivative. It's already 4:30. Okay, so then Laplacian of x mu equals 0. This becomes the alpha, x mu equals 0. Or if you write it in tau and sigma coordinates, well, tau tilde and sigma tilde, but let me call them tau and sigma. So this is derivative in which, so second derivative with respect to sigma minus second derivative with respect to tau of x mu equals 0. Sorry, not. Sorry. And this you recognize this equation, right? Waves, right? So this is the wave equation. So this says that this x mu, that there are waves on this worksheet. So we'll see more. We have to put the boundary condition to get the exact solution. Yeah, let me say. me say a couple more things. So the wave equation and then the constraint, which was T alpha beta equals 0, which is there. Then using that H alpha beta is eta alpha beta, what you get is that T00 is equal to T11 and is 1/2 of x dot square plus x prime square. And then T01 is x dot x prime. So the constraint is that these two things are going to be equal to 0. No, maybe I don't want to erase that. Let me erase this. This is indeed much faster. Now, as in the usual waves that you saw in, I don't know, it was called Physics 2 in my physics undergraduate class. So it's useful to define left and right moving coordinates, sigma plus and minus. Well, these are waves in. Define sigma plus and minus to be tau plus minus sigma. So that equation, the derivative is very easy to show. That the wave equation, so d alpha x mu equals 0, this becomes, or just saying that the eta alpha beta in plus minus coordinate has only plus and minus component. So this becomes d plus d minus x mu equals 0. So x mu splits into a function that depends only on x minus and a function that depends only on x plus. So x mu that depends on sigma plus x mu that depends on sigma minus, and one are left moving waves and the other are right moving waves. So why, for example, why this is right moving? So if you take the minus sign, for sigma minus to be constant, when tau increases, sigma has to increase. So those are waves that move to the right moving and depend only on sigma minus, and these are the left moving. Now let me pause now, because what I'm going to say is usually, it's a comment that takes 3 minutes, but it's very, very important. So let me say it after the 5-minute break. Any questions about this? Yes.
Is it obvious why the enduring field, metric,
Has one, sorry?
one positive and one negative?
Because, yeah, we take it on the worksheet. We want this to have a signature minus plus to be time. And the worksheet is like a two-dimensional conformal, well, conformal, no, I haven't talked about. It's a two-dimensional field theory, and tau and sigma are coordinates on the worksheet, but I want I want this to have signature, negative signature, and this to have positive signature. Then one can take Euclidean worksheet, which we will do after the break. But yeah, this is what I want to do. It's field theory in 2 dimensions, but with signature minus plus. Yeah, but I mean, yes, but then it would be, so you, I mean, yeah, you can have an Euclidean theory if you want, yes. Yeah, but let's choose that for the moment. Yes.
Yes, is it true that seeing the world sheet as an embedding in the bigger space is trivial if the background metric is conformally flat?
Let's, yeah, your question. So let's pause and let me talk about conformal invariance, and we'll come back to your question in 2 classes. Maybe. Yeah. Okay, let's take 5 minutes, so 4 until 4:40, 4:41. Yeah, sorry, 1 second. Let me. No. Shit, okay. So it's until what time? It's until 5:45, right? The class. So yeah. Okay, I'm a bit lost with time. Okay, so the break was. Never mind. Okay, so we'll use these coordinates all the time, the right and the left moving coordinates. But before going on, adding boundary conditions and seeing how these exactly fit, so I say I will pause and make some general comment. Let me do it here. So an important general comment that is valid for any metric, G mu nu. So how is it? Is it like, no, attention, yes. Important, very important comment valid for any G mu nu.
Sorry, I really think there's somebody waiting for you to ring the bell.
I did ring the bell.
Maybe they didn't hear it.
Ah.
I don't know if you want to have the honor of...
Do it again. Maybe it wasn't loud enough. One has to. Yeah, I did it here. Didn't go maybe far enough. Okay. Okay, so here we use local symmetries so we use diffeomorphism symmetries to fix the metric in this way, and then while rescaling to reabsorb this. But here, before the while rescale, yeah, there were many of you. So, okay, my bell wasn't loud enough, or was too close to here. So I said I'm going to, this is not the symbol, right? What is it, a triangle? An upside down triangle, yeah, it didn't, it didn't look this way. Okay, okay, better, yeah, now. Okay, an important comment that is valid for any metric G mu nu. So we use local symmetries to fix H alpha beta to be e to the omega eta alpha beta. to simplify our lives. But once we do this, is it true that we cannot do any more diffeomorphisms and stay within this gauge choice? And let's see, so if we do, so let's do some particular type of reparametrization. In which I don't completely mix tau and sigma. What I'm going to do is to do sigma tilde plus as some f plus of sigma plus, and sigma tilde minus as some f minus of sigma minus. So I'm doing a reparametrization, but that doesn't mix sigma plus with sigma minus. So it's a particular kind of, actually particular kind. There are an infinite number because it's f plus and f minus could be anything, but I'm not mixing sigma plus and sigma minus. So if I do h tilde alpha beta, this is the derivative of sigma with respect to sigma tilde, right? Sigma lambda with respect to sigma tilde alpha, derivative of sigma gamma with respect to sigma tilde beta, h lambda gamma. So the metric transforms like that. And this is, so this h lambda gamma in plus, so this is in tau and sigma coordinates, but this in sigma plus and sigma minus, what you have is eta plus and minus is it's plus 1 or minus 1, depending on how you, it's minus 1/2. Eta plus minus is minus 1/2, eta, well, this is equal to eta minus plus, and then eta plus plus, and eta minus minus are equal to 0. So this has only components plus and minus, and so what I get is the derivative of sigma plus with respect to sigma tilde, and the only one that enters here is the plus, and here the minus and the minus, because I'm not mixing plus and minus. So what I have, I mean, it's f inverse. Is this way or the other way around? It doesn't matter, but is this like this or the other way around? No, I forgot. Huh? It's the other way around, right? Yeah. Sigma tilde. So sorry, correct that in the also. I mean, it doesn't matter. It's but it doesn't matter. Of course, it matters, but not for the arguments I'm going to say. No, it was good before. Okay. Yeah, I had it good before in the, but yeah, in my notes here I have it the other way around. Anyway, the point is that this is so inverse of this is f plus or related to f plus. This is related to f minus, and this is eta plus minus. So so this is some function. So how did I write it? Okay, so this is proportional. I mean, this, this is eta plus minus, and this is, which is, and this is some function, let me call it whatever. So this is has f prime inverse prime, f minus, F prime inverse, F plus, F minus, inverse, prime. Doesn't matter, but it's some function times eta plus minus, which is, sorry, h plus minus, which is e to the omega, eta plus minus. And this is also an overall function. So h tilde alpha beta is e to the omega tilde eta alpha beta, right? So I call all this e to the omega tilde. So what I see is that if I do this particular kind of transformations, the metric is still proportional sum overall factor times eta alpha beta. So once I did these reparametrizations, it's not that I completely, I cannot do any reparametrizations and I go out of this case. I can still do these transformations, which are called conformal transformations. This particular kind of transformations that don't mix sigma plus and sigma minus are called conformal transformations. And this conformal transformation, so doing a conformal transformation, so a conformal transformation is the same as so a reparametrization of the sigma tau parameter, but that doesn't mix sigma plus and sigma minus, is equivalent to or amounts to a Weyl symmetry. Right, it's like doing a Weyl symmetry by this overall function. And the Weyl symmetry or amounts to do a Weyl, let's say a Weyl transformation, not a Weyl transformation. But this is a symmetry. A Weyl transformation is a symmetry. So these conformal transformations are a symmetry of my theory. So I can do any reparametrization that mixes sigma plus and, that doesn't mix sigma plus and sigma minus, and whatever I have, this overall function, I reabsorb via a Weyl transformation that is a symmetry. And this is so first these conformal transformations, they are, so if you put conformal transformation on Wikipedia, I'm very bad at drawing, so that's why I put this. So these conformal maps, they preserve the angles, but not necessarily the lengths. So a conformal map is a function that locally preserves angles, but not necessarily the lengths. And then you have more formally all that with only this is a conformal transformation. And actually it's so I can rescale, that's a conformal transformation as long as I preserve the angles. So that conformal transformation is a bit more less trivial than a rescaling. But this is a very, this is a very important property. And it's so if we go to, if you use complex coordinate an Euclidean worksheet, now, so the question whether I choose Euclidean or Minkowski metric here is, I can do sort of a weak rotation, define tau to be IT, and then sigma plus, which is sigma, which is tau, so this is IT plus sigma. And if I do minus sigma minus, this is minus IT, minus IT plus sigma. So if I call this complex coordinate on the worksheet C, this is Z bar, Z and Z bar. So a conformal transformation is a holomorphic function. So it doesn't mix Z and Z bar, so a conformal transformation is some function, is some Z tilde, is a function only of Z, but not of Z bar. So this is Z tilde, right? And there is an infinite number of such functions. So that's why we say the worksheet is a conformal field theory. So it's a field theory that has this conformal invariance, these conformal transformations. You can reabsorb them via a Weyl transformation that is a symmetry. So string theory is a two-dimensional conformal field theory. And you will have classes starting from Friday on conformal field theories, which is great. And this is almost all I'm going to say about conformal field theory. But, I mean, Dalimil will talk about conformal field theories in general dimensions, and then he will go to 2 dimensions, and you'll see 2 dimensions are special. But so string theory is a 2-dimensional conformal field theory of these scalar fields. So these are these x mu. And in some sense, this is string theory. So if you have a 2-dimensional conformal field theory of these scalar fields, then whether you can interpret these scalar fields as embedding coordinates of some worksheet in space-time might not always be possible. But one can say this is more fundamental. This is string theory. So eventually maybe there's a manifold or maybe not, but this is a theory. This is a theory that will give you gravitons, that will give you quantization of gravity in something which, so yeah, somebody was asking, for example, in string theory there are some dualities that you will see, and sometimes in one frame you can interpret these as strings in some background metric, and then you do a duality and you don't have that interpretation anymore. But these dualities are perfectly fine, are symmetries of string theory. So the fact that you cannot interpret this other theory or this dual frame as strings moving in some space-time doesn't mean that it's not string theory. It's as good as a string theory as the original one, where you see that these are strings moving in some space-time. So yeah, one could go on and forget about this as embedding coordinates and go on and do conformal field theory, conformal field theory, conformal field theory. But it becomes very abstract. So that's what some books like Polchinski's book is like that. And then when you don't have this interpretation of this as embedding coordinates, it becomes really abstract. So I prefer to interpret this as embedding coordinates, go back to flat space, and go nice and easy. But yeah, I mean, this is what string theory is for. Okay, I guess you're more tired because when I said that, I got many people complaining, asking. But okay, we can discuss. I mean, this is an important point. We can discuss more tomorrow in the question and answer session. I mean, well. Okay, so let's go back to our easy. So back to G mu nu equals zeta mu nu, and the equations being d plus d minus x mu equals 0. So free d scalar fields, x mu left of sigma plus x mu right of sigma minus. And now to see what these are, I have to add the boundary conditions, and the boundary conditions now will depend whether you are doing closed or open strings. So if we do closed strings, so the boundary conditions are that x mu at tau sigma plus pi, and here I'm using the conventions of Becker-Schwarz, which are not very nice. But yeah, I try to be consistent. So the string, the parameterization, you take a parameterization in which sigma goes from 0 to pi, and they use the same for the open and for the closed string. I think it's much better to do sigma plus 2 pi, but then it's a nightmare of conventions. If I like this book, then better follow that book. So well, I didn't write the boundary conditions, but of course this you guessed it. So these are the boundary conditions for the closed string. So 0 and pi are the same point, so the embedding coordinate should be the same. So with those boundary conditions, then x mu left and x mu right. So let me write it, and then I'll go slowly. So this depends on sigma. This depends on sigma plus, and this depends on sigma minus. Okay, I'll let you write, and then I explain. Sorry? a lower, okay, maybe let me do this. Okay, and I think we're ready. I'm ready to erase the Polyakov action. You already know it by heart. Okay, so what are all these objects that we introduce here? So first, remember that x mu is the sum of the two. So if we sum this little x mu, that is a constant, doesn't depend on tau and sigma, this is the center of mass position. So the string is at, the center of mass is at some point in space-time. If you add these two, then what you get is alpha prime p mu tau. So this p mu, small p mu, is the center of mass momentum. So it's at center of mass position, it's moving, and then it's oscillating. So these are the oscillation. The amplitude of the oscillation is square root of alpha prime, which is L string. So the amplitude of the oscillation is of the order of L string. So it's a tiny oscillation. And this alpha mu n are the modes. So in general, when you write plane waves, you write so a n, or you can write it as cosines or sines, tau plus sigma plus bn sine of tau plus sigma, well, actually of 2. So here we wrote it in complex coordinates, and these alpha are like the an and bn. It's just that the amplitude really goes in this L string, so these alphas are dimensionless. So they are either, you can think of them, they are either 1 or 0. It tells you, so the ones which are non-zero, it tells you where, in what direction the string is oscillating and with what frequency. So n is like the oscillation number. So the string is oscillating. I mean, I can't, well. Yeah, it's easier to do it with a closed string, but it's oscillating to the right and to the left. So there are modes that go right moving, oscillations that are right moving, oscillations that are left moving. And with a typical amplitude that is L string. And then also, if I want x mu to be real, then alpha mu minus n should be alpha mu n complex conjugate, right? You can put this. So because I didn't put cosines and sines, it's simpler to do the exponentials with an I. Then this I need to have this relation. Okay, that's clear. Yeah. I mean, it's like wave mechanics. And for an open string, now for an open string, sigma equals 0 and sigma equals tau are not the same. Are not the same point. So what are the boundary conditions? If you remember wave mechanics, it's the same. You remember? Right, you can have, I mean, a few answers at the same time, but I think, so you can have either Dirichlet boundary conditions, and that means that one end is fixed, one or the two ends are fixed. So let's say x mu, x mu of tau 0 at sigma equals 0 being some x0 mu, and x mu of tau pi, which is the other end. So, sorry, sigma equals 0 and sigma equals pi. This is some x1 mu. So here I'm attaching these are fixed, these are the Dirichlet, or you can have Newman boundary conditions, which are, if I let this oscillate, this will not do this, but it has to, it's something like this, which is that the derivative along sigma of x mu at tau 0 is equal to 0, and the derivative along sigma of x mu at tau pi is equal to 0, right? This has to come like this if I let it oscillate freely. And one can have mixed Dirichlet-Newman boundary condition. For one end have Dirichlet, for the other have Neumann. So I can fix this. I can say that this is attached to this, and this end is free. And then also here, so if I put some object like that, means I put in Dirichlet boundary conditions in this direction, but not in this. So I'm letting it move freely in this plane, but I'm attaching it in this orthogonal direction. So I can have all sorts of, so mixed Dirichlet and Newman boundary conditions in different directions and for the two ends. And each, depending on the boundary conditions, then the solutions, you have a different solution, and I'm going to write the solution for Neumann boundary conditions in all directions, and in the exercises you have to play with Dirichlet boundary condition or mixed. So this is for Neumann boundary conditions. So the derivative with respect to sigma is equal to 0. So one thing that is very important is that these boundary conditions mix sigma plus and sigma minus. If you write this in terms of sigma plus and sigma minus, either this or this, because derivative, this one is easy to see, derivative with respect to sigma is a derivative with respect to sigma plus minus derivative with respect to sigma minus. So this mixes, all these boundary conditions, they mix left and right. So in the open string, we don't have independent left and right moving waves, but what we have are standing waves, the same as for ordinary strings. And so for Neumann boundary conditions, alpha prime p mu tau plus 2i. Here I have cosine of n sigma. So the derivative is the sine of n sigma, and then it vanishes, the derivative with respect to sigma, and then it vanishes at 0 and at pi. So for Neumann, I also have a center of mass position, can be anything. I also have a center of mass momentum. And of course, this will be different if you have a Dirichlet boundary condition. If you have a Neumann boundary condition, it's free to move. And the oscillations, so single set of oscillations. So and so this is easy. For example, if you have n equals 1, this is just the cosine of n sigma. And this keeps, so it goes up and down. So so let's say this is at tau equals 0, and then it oscillates, it goes up and down. So if you have n equals 1, and then let's say this direction is, so if you just have alpha 1, and let's say this is x1, alpha 1, 1, well, I mean, you understand, right? If you have n equals to 2, it's something like this, it oscillates like that. And you can, the oscillation can be in this direction, or a linear combination in directions. That's what, which ones of these are non-zero will tell you what are the directions in which it oscillates. Okay, so far so good. Now, since you're tired and you're not going to complain, quantization. I never know whether to write the American or the British way. Okay, American. Quantization, and as I mentioned, we're going to do first quantization, as in quantum mechanics. Second quantization will be doing string field theory, and it's a quantization of an infinite number of fields. It's very complicated. It was discussed a while ago, then couldn't get too much out of it, and now people are coming back to it because there are certain things that you can do doing string field theory, but it's complicated. You can do research, you can do your PhD on string field theory, and then you will learn string field theory, but in a course in general, it's not taught. And I shouldn't say anything bad if any of you is doing a PhD on string field theory, or is going to do. You are, okay. Good luck. No, it's nice. Now they're getting nice results. So now it's, it was sort of sleeping for a while. So no, and it's not that horrible. But okay, it's not for it's not for a basic course. So quantization, what does it mean? We're going to promote this, and this to operators. So all the blue things to operators. And they will be such that x mu p nu, this is, well, an h bar that we put to 1, I eta mu nu. Alpha mu m with alpha nu n, and the same with alpha tilde mu m alpha tilde nu n. This is equal to m eta mu nu and delta m plus n 0. So the only ones that have a non-trivial commutator are alpha m with alpha minus m. The others just commute. And then alpha with alpha tilde commute. Alpha mu m, alpha tilde nu n, this is equal to 0. And these commutators, these are such that, I mean, you can actually do reverse engineering because what you want, so these commutation relations are such that you have this commutator of big X mu of tau sigma with big P nu of tau sigma prime. So this is an I h bar, so I eta mu nu, delta of sigma minus sigma prime. And this P nu, so this is a derivative of the Lagrangian with respect to x dot mu. So with respect to the x mu d tau. This is an exercise to show that if you do these commutations, relations, then you get this equal time commutator, and where, so somebody asked about locality, so you get a delta of sigma minus sigma prime. So they have to be at the same, I mean, this is non-zero with for sigma equals sigma. So in quantum mechanics, you just have tau. So you're not used to this kind of thing, but so then you get this delta of sigma minus sigma prime. And then that commutation is nice. So if you define, so defining A mu m to be yeah, 1 over square root of m alpha mu m and A dagger mu m to be 1 over, so this is for m greater than 0, square root of minus m. No. Alpha mu, sorry. Alpha mu m. So I'm sorry, alpha mu mu. Yeah, this would be a mu minus m. Yeah, so minus m is positive. So if you do this, then what you get is that A AM, AN dagger is eta, so mu and nu, this is eta mu nu delta mn. And this is just the commutation relation of the oscillator algebra in quantum mechanics. So up to this normalization in the commutator, but if you absorb this normalization, then these are just creation and annihilation operators. So the one with negative, the A dagger, so alpha, now let me write it, alpha mu minus n are creation operators. And the conventions are a bit weird that the minus are the creation ones, but in that everybody agrees that the minus one are the ones that create, and the alpha mu m, so now m is greater or equal to 0, or we'll see the alpha 0. And these are annihilation operators. So one starts as in the basic quantum mechanics exercise. One starts from a ground state that is annihilated by all the annihilator operators, and you act with creation operators. So define a ground state 0 such that so alpha mu m on 0 is equal to 0 for all m greater than 0. So it's annihilated by all the annihilation operators, and alpha tilde mu m on 0 is equal to 0. Then state phi you create by acting alpha mu 1 minus m1, alpha mu 2 minus m2, etc. Alpha tilde mu 1 minus n1, alpha tilde nu 2 minus n2, etc. on this. So I act on this, and then I can write a polarization tensor, so I can create an oscillation. Let's suppose I have a single alpha oscillation. It can be in different directions, and the way, so if I have only one minus m, I can write, so this would be the polarization vector. So in general, I have a polarization tensor. So E mu1, mu n, or mu, I don't know, depending on mu1, mu j. So suppose I have j of these, I of these alphas, and j of the alpha tildes. This just tells me in what directions I'm doing these oscillations. So I start from the ground state, and then I generate oscillations in different directions, moving, left moving and right moving. And if it's an open, so this is for a closed string. If it's an open string, you just have this, the left moving ones. Okay. Now, whenever I did oscillations, I always so oscillate in x1 direction or x2 direction. Can I have an oscillation in time? So can I create a state that is alpha 0 minus n on 0? Is this state allowed? There's something weird about this state, creating an oscillation in time. No, why not? Negative norm. If you compute the norm of this state, so if I call phi to be the state, then phi is 0. So here I have alpha mu minus n 0. And then I have to make this act on the left, but then on the left is the dagger, so this would be, sorry, not mu, 0. This would be alpha 0 n. And now I can use the commutation relations, and this is 0, eta 0, 0, n 0. I mean, well, or I can put this outside of the, plus the other way around, but alpha n annihilates this, so it's just this, and this is minus n, well, 0, 0. So, and in general, this is taken to be 1, so if you take this norm to be 1, then this will be a negative norm state. And negative norm states are very bad. You lose unitarity, causality, I mean, everything, all hell loses. So this shouldn't be an allowed state. And where am I going to see that this is not an allowed state? I'm going to see it by the constraint. So we have quantized things, we have solved the equations of motion, but we forgot about the constraint. So remember there was this constraint. And this negative norm state will go away once we impose the constraints. Okay, so let me do the constraint. So the constraints were that T alpha beta is equal to 0. And we wrote this in T00, T11, and T10. But if we write them in terms of plus and minus, what you get is that there are only two components, T plus plus and T minus minus. And this is D plus X mu, D plus X mu. And here I'm actually raising and lowering with eta mu nu. Well, again, this could be general. It's true that this is general and I could have a G mu nu, but all I said before wasn't general. So, so here you can think of this as raising and lowering with eta. And this is D minus X mu, D minus X mu. So let's see how this look like. So let's take D plus X mu. I erased the solution. So let me write the solution for the closed string. X mu, so which one the plus is the left, so x mu left, that depends on sigma plus, was 1/2 x mu plus, let me copy, I don't want to, I mean, the coefficients will not be important, but let me try to, so alpha prime p mu tau plus sigma, sorry, plus I square root of alpha prime over 2, sum over n different from 0, alpha mu n over n, e to the minus 2 I n tau plus sigma. Okay, so the derivative of this with respect to sigma plus is alpha prime p mu plus square root of 2 alpha prime, the sum n different from 0, alpha mu n e to the minus 2 I n sigma plus. And I hope I have all the factors right. Yeah, I think I have all the factors right. Yeah. So now if I define, so let me define, the original sum was for n different from 0, but once I have the derivative, this 1 over n goes away. So I can write this as a single sum. If I define alpha 0 mu to be square root of alpha prime over 2 p mu, center of mass position, then this is all square root of 2 alpha prime, the sum over all n, alpha mu n e to the minus 2 I n sigma plus. Right? Okay, so if I do, so I have to do d plus x mu square, so d plus plus is d plus x mu square. So I'll get 2 alpha prime, and then I get a